Okay, folks, I'm going to go ahead and get started now. Another colleague of mine from the EFF is going to be joining us here in a few minutes. My name is Eric Blossom. I got started, first of all, what GNU Radio is about, in case you think this is streaming audio, this is not streaming audio. This is like radio, like the old-fashioned radio wave radio. When I came up here, I noticed someone had placed the radio frequency spectrum up here. I don't know where this came from, but I think it's kind of interesting that it's here right now. How I got started in this is I spent about the last 8 years working on secure telephones. And as a piece of that exercise, I did a lot of work with cell phones and looking at what are the vulnerabilities there. There are a lot of vulnerabilities in the cell phone network that you could identify just by reading the specifications and thinking a little bit. But there's nothing like being able to demonstrate them. So I had a motivation for, I'd really just like to be able to get the bit stream off of the air on a lot of the protocols. But it turns out that the test equipment is either very expensive, or you've got to be the right person to have the test equipment and all this. And so I had this interest in, well, how do I get the bit stream off the air? Then what I discovered was that there really weren't too many sets of tools available for experimenting with all of these new digital modulation strategies. So I looked and said, okay, what do we got out here? There's like MATLAB, there's some tools, there's some actually quite expensive but really also fascinating stuff. There's some people building hardware that's specifically for experimenting with software radios. And but what I noticed with one of them is that the hardware was sort of in the realm of reason, maybe like $10,000 to $15,000 kind of a thing. But it took another $100,000 worth of software to put the whole package together. These are the guys that like Lyre signal processing are selling, which has got a big FPGA and DSP and all this great stuff. But oh, you need a set of Xilinx tools. You needed like 5 people's sets of tools to really make the thing fly. I gave a variation on this talk to the folks at the Copy Protection Technology Working Group. It's the Motion Picture Association of America, and this was, I thought, the most appropriate quote I could come up for them. Because it was like, our big pitch here is, it's innovation. We're not saying that we've got the best way to do it right now, but we're clear there's a future that has to do with innovation and flexibility and all that. And, personally, I'm not invested in preserving their business model. I think it's great they're doing whatever they're doing, but let's not let... We start to get in trouble, and we'll talk about this more a little later, when they start pushing for like regulatory enforcement of their business plan. So, this is Ladrina Cherney. She's an intern at the EFF. I don't think that mic, you can try that mic.
Tap your mic. Oh, there it is.
Sorry, is there here?
Oh, no, I just found your mic.
Just keep talking. You should introduce yourself.
Hi, well, my name is Ladrina Cherney. I'm an intern with the Electronic Frontier Foundation. And the EFF is one of the only organizations to be observing the BPDG process.
Speak into the mic.
They're one of the only organizations to be observing the
right.
process,
there we go.
The Broadcast Protection Discussion Group. And so a lot of things that are going on in that group are going to affect GNU Radio and open source. So.
Great. Okay, so the topic I think that's in the program is something about free software radios collides with Hollywood. We're gonna get to that pretty much at the end, but I really want to cover sort of the technical motivation for this, what this is really about. I'm probably going to be preaching to the choir a little bit on this, but here's kind of the basic outline that I'm going to try to cover here. Software-defined radio in general, what is it, who cares, why, what's this about, how is this different than anything else? Free software, this is definitely, I'm probably preaching to the choir, but who knows, maybe there's folks in here who haven't signed on, or why is this a good thing? GNU Radio specifically, what we're trying to do in the grand scheme of all the software radios area, what piece of it are we doing? We're specifically working on it at ATSC's Advanced Television. The NTSC was the old analog TV. ATSC is the digital TV. It supports potentially high definition TV. It's Standards Committee. Okay, very good. And P.S. If you've ever looked at the standards, they're like the worst standards I've ever seen. If anybody here really has got the secret decoder ring for them, happens to have test vectors or anything like that for them, please come see me. But that's digital TV, which is currently actually enabled and being broadcast in many of the major metropolitan areas in the U.S. today. There's some high definition content on it, but mostly there's nothing particularly exciting. You might have some primetime shows in HD. Anybody here have a digital TV receiver or a card? All right, so we're the technology leadership, and there's like 3 folks here. This is the benchmark. Okay. We're going to talk a little bit about politics, and then we'll cut over and really we'll take a look at some of the code. We'll do pretty much any kind of technical Q&A, because it gets to a certain point, there's like the hand-wavy part about this is software radio, and well, what does the code look like? I regret that I wasn't able to bring the actual hardware. We'll talk a little bit about what we're running it on, but it's a desktop dual processor F1 and some RF hardware sitting around it. Software radio in general is about really, we're trying to turn all this stuff that used to be a hardware problem into a software problem. And the I think of it is just trying to get the software as close to the antenna as feasible. And what's feasible, varies depending on the year and how far we're going. There's some amazing stuff happening with regard to the fact that commodity processors are getting really, really fast. I mean, we are one of the few people that I know of that has a real application that can just consume MIPS and bury processors. I was speaking at the Asilomar microcomputer workshop a few months ago, and there was really great group of people, but they have the current architects from Intel, and also at the same time the current architects from AMD, and this is all off the record conference, and these are the guys working on the 30 to 100 gigahertz processors like today, and they're like, great, we like what you're doing, you would give us a reason to exist. So what we're about here is software defines the waveform. To do ham radio operators, anybody? Okay. If you think about regular things that we think of as radios, there's traditionally been traditionally it was all analog systems. So I had my FM radio or my AM radio. Or if I looked at early pagers, there was analog, it was pretty much analog circuitry. If you look at early modems were that way also. I mean, you had this, the 110 or 300 baud FSK modems. It was all analog hardware. There was a piece of hardware that did a specific job. What we're trying to do is get into a situation where really everything is defined by software. This includes, is it AM or is it FM? This is, am I doing, PSK modulation? The whole thing we're trying to get done in software. And we'll talk just in probably the next slide about why. And again, we're trying to get rid of some of the analog signal processing with DSP. And this is the standard reasons for doing DSP is that the hardware is reproducible. There's nothing to tweak. When you build analog hardware, you've got this whole problem of component tolerances and all this. There are certain filters, for example, when you want 2 identically matched ones, it's just you really can't do it in analog hardware. They're going to be slightly different. And if you do it using DSP, the math is like perfect, right? It just, it says multiply by this constant, and it's the same constant on both sides. So it turns out there's some algorithms that you can implement using digital signal processing techniques that you just really can't do with the analog. Okay, why would anybody do software-defined radio? And kind of the other question is, well, how come everybody isn't already doing it? What you're going to get out of this is flexibility. This is where we're headed. The holy grail for this stuff is radios that reconfigure and just do the right thing. So if you can think about the future is an idea where you've got a PDA of some kind. It's kind of the PDA, cell phone, pager, TV receiver, shortwave receiver. It's the device that kind of looks around and says, oh, look, I'm sitting in this coffee house and I see, looks like 802.11b. Wow, it's wide open. I'm free. Let's go. Okay, I got connectivity. Or it's like, no connectivity here, and there's a request in for internet connectivity. Well, let's see, I've got GPRS, cellular connectivity. I can push packets over that. So the idea is ultimately we get to a situation where you have hardware, you have one hardware module, and depending on the software that's running at that instant, you have a whole completely different kind of transceiver. Now, we're not there yet. But it is going to happen. Those of you who know something about, sort of RF stuff, there's actually also some really interesting stuff happening in the MEMS arena, the micro electromechanical systems, these ones where they basically use IC design techniques, except they're building little mechanical gadgets. It turns out there's some really cool RF hacks you can do with that actually get rid of these problems about, well, I've got the wrong antenna. How can I receive both 2 gig and 4 gig? Or how about, how do I get this? And they've actually, currently there's a bunch of startups that are working on this. And again, it's not too far off. This multiple personalities thing, it can turn into whatever I want to turn it into. One of my favorites is You know, I carry a GSM cell phone. It's got this great feature set and everything. However, I was driving across the country, and I happened to be in Kansas. And let me tell you, there are like, you know, from one border to the other on I-70, there is no coverage. And it's like, well, gee, you know, if this thing could do CDMA, or if, let's say that it could also just run at the 800 megahertz band, and it could fall back and do amps or anything else. There's really, this is the idea that we will have devices that are able to on the fly reconfigure themselves. And of course, I'll need a contract with the operator or whatever, but big deal. I'd like coverage, please. You know, this idea that I now have to, I'm in Kansas, I have to go to a payphone is a little odd. So now, with software radio, there's also some stuff that you really can't do with traditional analog design. And one of the cool things, and it's part of the things I'll talk about in what we've got working right now, is that you're able, with one RF front end, to actually receive or transmit multiple channels at the same time. One of the demos that we got and that we put together at the beginning was some software that tunes into the regular broadcast FM spectrum. And we're currently demodulate 2 FM stations at the same time. It's kind of this, you know, kind of little tiny semi-hack where we take, you know, $5,000 worth of hardware and we do what you can do with 2 $5 radios. But it's cool because the thing is actually the RF section is tuned to one big chunk of about an 8 megahertz piece of the spectrum, and we can pull out pretty much as many radio stations from there at the same time without missing anything. So if you happen to have been a surveillance-minded person, this means, for example, that you could watch, hypothetically speaking, all of the paging channels plus all the traffic channels all at the same time on certain digital communication systems without missing anything. You know what I mean? So you can watch the paging channels, you can see all the calls set up, plus you can watch all the traffic all at the same time with one piece of hardware. The idea with this, where you get better spectrum utilization, is about, well, I could build these radios that were smarter. I mean, today we really design, and if you look at a piece of the regulatory regime that we're under with the FCC, and there's lots of people who have lots of rants to do about them. I'm not really going to go down that path right now. You could talk to Dwayne Hendricks. You could look at the open spectrum stuff. It's on I think it's read.com. Some really great stuff about, you know, why the FCC has really got the wrong model for these spectrum auctions and things. But what you could do is you could build radios that, for example, were designed around the idea that I got a smart radio. It's going to know that it's operating in an area where there's lots of quote interference, and they would still perform. It's the idea, instead of building a really dumb receiver that says, listen, there can't be anybody else talking right now, I build a smart receiver. You can think spread spectrum, things like this, where it all looks like interference anyway. This would allow stuff for, a friend of mine said, well, this would be more like you design your radios for jam margin and, you know, let the most clever radio win. I mean, it's a whole different way to approach it, but it gets rid of this question about, do I need some entity that's selling off pieces of the spectrum or licensing them or whatever. We start looking at areas where there's not that much opportunity for innovation. I'm personally not a ham radio operator. I mean, I'm an electrical engineer by training. I've read through the manual. I should probably just trot on down and call the guys and go do the test. But I keep looking at, you know, man, they're not exactly on the leading edge. These are people who are doing, you know, they're doing FSK on top of FM. This is, you know, it's like, why did you go that way, people? Then the idea with cognitive radios are ones that are, this is kind of really kind of on the bleeding edge. The military guys are really hot on this, and the idea is that you could kind of go look at the spectrum and see what's not being used right now, and you take advantage of it. So you've got some way to talk to all your people in your little ad hoc networking. So it's kind of all the ad hoc questions that we've seen come up in this fisheye routing and all this, so how do I build my network and how do I move it around? But if you have that the RF piece is also, like, can be changed on the fly. It was like, hey, there's like nothing happening over here. I talked to a gentleman, I know we're in New York City, it's kind of a sensitive topic, but there were, I talked to a guy who had a spectrum analyzer on the air pretty much right after the towers went down. And they said that, you know, the people with cell phones couldn't get through. But if you looked on a spectrum analyzer where there was action in the spectrum, there's like this little piece that's just jammed, and then there's a big spaces that there's nothing going on. And this is a situation where things like cognitive radios, that we really kind of look and see, what have I got going, what can I do, and take advantage of it on the fly. You all use DSL that day, yeah?
Okay, well.
Wow. Right. Okay, how come everybody's not doing this? You know, if this is so great, well, the solution is it's actually considerably higher power than the dedicated ASIC. So, for example, the reason, you know, our cell phones, I like personally the fact that I don't have to charge it more than once a day, and I can talk for, you know, pretty much as long as I want, and it still works. Now, if I happen to be burning, you know, like 5 watts in here, that's going to be a different story. But what's going to happen, and so we need more MIPS required because there's not, you know, I'll talk, we're doing this on dedicated hardware that's really amazingly fast when you get right down to it, and but it takes more MIPS to do it on the general purpose hardware, and it costs more. Okay, who's currently hot on this SDR stuff? The military. You know, like a lot of good stuff that we all like the internet and stuff, they thought that was a pretty good idea. Their driving situation right now is talk about legacy interoperability problems. Here's folks that have got all these different branches in the military, different divisions within them, different countries, trying to interoperate with everybody. They have a situation where they'll have really a giant rack of radios. And they want to talk, I mean, in this, the Desert Storm stuff, there was all this, you know, Desert Storm, it turned out that of all of the traffic that could have been encrypted, there was only like, something like 5 or 6% of it was actually encrypted because of an interoperability problem. So you got all these problems. You got a stack of radio, you got some poor guy in the field, they really want him to be able to carry one radio that can talk to all the people he needs to talk to. So if they could build radio, and this again was, they did, it's been about 5 years ago now, they did some early prototypes on software radio, and I think they did the right thing, is they took they built a card cage, they put a bunch of DSPs in them, and they made it work. Now, you know, the idea at that point, and it's really the same argument that we're making here with GNU Radio right now, is that we know this hardware is going to get faster and cheaper, and we don't even do anything about it. So let's get the math all worked out. Let's get the basic infrastructure working. We're going to get the free ride that, you know, AMD and Intel and, you know, everybody doing the PowerPC or whatever is taking care of for us. The other place where you're going to see my prediction on where you're going to see it first is cellular base stations. So you've got this thing where, you know, in Europe, they have pretty much the sense that everybody uses GSM or GPRS, but they're basically compatible, reasonable upgrade path. In the U.S., we've got the legacy AMP stuff, the analog cellular. We've got the U.S. TDMA, IS-136. We've got the CDMA, which is IS-95. Plus, we've got some GSM stuff. Plus, eventually, we'll have GPRS. You know, some folks are dreaming we're going to have 3G someday. Who knows? But what you've got is like an operator like AT&T Wireless, which currently in my neighborhood out in California is an IS-136 provider. Now, AT&T is not stupid. They understand that GSM into GPRS is a lot better path for the future, including if they ever do go to 3G, it's a much better path. You get to where we're actually pushing packets across here. But today what that takes is they really have to go, you know, get the forklift out, throw all that equipment out, put new equipment in. But they got this problem is they're not going to transition their entire customer base in, you know, one day. They don't want to, you know, really you prefer those customers buy those new phones on their own for some new feature, right? So what software radio will allow them to do is, if you think about it, on some of these, they're all both operating, for example, in the 800 megahertz piece of the RF spectrum. So the RF gear is all identical. It's really, in one sense, a different set of protocols, different set of modulation strategies for the air. So the software base station, it would be possible on the fly to dynamically alter your allocation of processing power. So it's like depending on how many, you know, IS-136 users I've got at this instant versus how many GSM users I've got in this instance, I can dynamically partition this thing. I mean, as software people, we go, but yeah, but of course. But that's traditionally not how it's been done. Part of the problem today with how come our cell phone system seems to be lagging behind every place else, I mean, how come we don't have GPRS here? I think in New York City it's actually available, but, you know, in California we don't have it. And this problem about it's hard to roll out new things. If they get to a base station architecture that's really more of an open, you know, there's software pieces you can just upgrade and the thing does some new tricks, then that's better for everybody. That's more to the new features on the market quicker. Okay, this was the kind of the future here. There's personal communication devices, and I have talked to a bunch of different people here. I like this idea that I can get connectivity wherever I am. That, like as the future, I have talked to some people who really want to build, like, I mean, it's kind of like if you take that idea about people wanting to build those slate PC kind of a things. You know, I got the slide and the pen, and maybe the pen's got the little MEMS accelerometer in there, so there's like no wire and it can tell how your hand's moving and all this. And I mean, there's like people got some ideas for some really cool stuff. So I've got something that looks like a ballpoint pen, which is really a device that conceptually, could handle all the RF communication, the whole 9 yards. This is the kind of thing that people are really thinking about right now. Now, in a little shorter base thing, kind of the stuff we're doing here is this idea that you could have a generic transceiver. And we're saying PC-based. I mean, we're mostly meaning kind of commodity, off-the-shelf stuff. This could be something you would have at home. It could do your radio, your TV, your high-definition TV. It could be, it's got it's got you and all your neighborhood's music collection on it. It's plus you get to work in these unlicensed RF bands. One of the things that's interesting about the quote unlicensed band is they're not like complete like free-for-all. There's some power restrictions on them. Depends on which of the bands. Some of the quote unlicensed bands really have an enormous amount of baggage around them that seem to only help a certain couple of people. We all like the 2.4 gigahertz piece of the unlicensed band, which is where all of our wireless stuff that we're currently deploying is using. There's another chunk up at about 5 gig, which is the 802.11a is going to go in. Back in the 802.11b, just in the sort of things that people aren't really thinking about department, apparently in Washington, D.C. right now, actually across the country, that same spectrum is available. It's the industrial, scientific, and medical equipment, ISM band, and they're building what are called microwave lighting. And apparently it's currently deployed in parts of Washington, D.C., and in places where that is turned on, forget your waveland, man, it's not happening. So what they've basically got are these street lights that really look like they're a klystron out of a microwave oven surrounded by gas, and they just accelerate it and the thing illuminates. And it's like 30% more, the reason is because it's 30% more efficient than whatever they've got. But the problem is you got a 100-watt transmitter that's basically this broadband jammer that's, called the street light. So there's some parts of this unlicensed band that, people aren't really, it's not all sorted out. The other thing kind of on just another kind of technical detail, if you look up at 1.9 gigahertz, there's another piece of unlicensed band, and it turns out if you look, it happens to be right in the middle of the PCS band. So you've got the PCS band is like there's A, B, C, D, E, F. It's sliced up to different carriers, but effectively there's a big chunk over here that's for the base station to the mobile, and then there's a chunk over here that's for the mobile to the base station, and then the unlicensed band is right in between, which is really quite. It's pretty cool. It turns out that you can't really use it, however. You got to buy in. I can't use it. I can't. You got to buy into some consortium that's got to buy out some incumbent point-to-point microwave relay, and there's some restrictions on what you can do. Who it really serves are some of the cell phone operators who, it works great for them. It means they get to use the spectrum. If that spectrum's not jammed, or if their spectrum's jammed, or if they've got people that don't really have a high quality of service requirement, they can use pieces of the unlicensed band. Because it's right adjacent to their stuff, they can go over and work on that, and then, well, if it looks like it's starting to get too much jamming over here, well, they just move them back into the spectrum that they paid for. So anyway, I recommend, if you haven't ever, read some of this FCC regulations. They're mostly on the website. They're in pretty much more or less plain English, and you can read like about 2 paragraphs and go, wow, how did that get there? Whose interest did that serve? Okay, this is in the preaching to the choir department, but I talked about the specific thing in front of the folks from the MPAA, and also a large group, in the audience included a large number of Japanese engineers who, this idea that people would actually write things, create intellectual property, and then give it away was so far over their head, they just could not believe that. And without naming any names of any people or any companies outside of the fact that they were Japanese, they were saying, software, radio, TV, a very, very professional engineer. It's like, would never give it away. We're like, sorry, different culture. We got ways to win with this. Very interesting. So this is free as in liberty, not the free as in beer. And the other piece we pitch, it's a culture of innovation. This is where the whole free, open source, free software movement, the whole hacker thing is all about a culture of innovation. This is like, what's out there? How can I make it better? How does it work? How come it works that way? How can I make it some other way? And then the various licenses. And where we come to with this, and a little later I'll talk on, is how come we're doing an HDTV receiver? I'm a guy who watches, like on a good month, I've got 2 hours of TV time. I'm like the last person, I'm one of those guys that never had a TV that only was hooked to a VCR. And now, why am I spending hours doing, building an HDTV receiver? Well, there's a political point to be made. And this, part of what we're up to is we want to build devices that allow you to do what you want with this stuff that's being broadcast. Personally, I think it's a crime. I mean, if you think, look, what we know about software, we know how to make things do what we want. With digital TV, I'm kind of getting off slightly out of order here, but I'm going to do it anyway. What's really happening with digital TV is they've got some transmitter somewhere, and it's got some modulation strategy, but what comes out of the receiver really is an MPEG transport stream. It's multiplexed down, it can have multiple programs in this one 19 megabit channel. And it's all perfectly already compressed. This is like TiVos and replays. Part of the problem with them is they have to have all this hardware in there to compress the signal. Well, if you think about this, let's say I built an ATSC receiver. Well, what I've got is compressed MPEG coming to me all forward error corrected. Everything is really cool. It's got program information in there. I think we're going to be able to tell when they're cutting to commercials also without any fancy stuff. So, of course, our first thing is hello, and then we plug it into what is it, XINE, Zine, Zine. I don't know how the conventional pronunciation is, but we built a little glue that goes between our output is going to be this transport stream for ATSC, which is MPEG, what is it, main level, And it basically looks like the DVD stuff, only it's a little different. But it's not too much software to take our output, mangle it around a little, and pipe it in. They have some extensions that are in here that include things like directed channel changes, which is where they want to do personalized ad blasting to you, based on your zip code or something. So we figured that ought to be real easy to just, oh look, directed channel change, no thank you, So part of the excitement for us is we can build the killer TiVo here with really almost no effort. Once we get the receiver done, all the rest of the stuff is oh gee, copy it to the disk. Okay, spool. All right, good. Now play back. Pause. Okay, this is the easy part. Free software. We all know this. Hey, it's worldwide. I do my pitch to the corporate folks. No, people like IBM are doing Red Hat, Mandrake, publicly traded companies. Or look at those billboards all over Silicon Valley that have I love penguins. Linux, talking. Yeah, see, the people are making money with this. Apache web server. This is not a fringe activity. Okay, GNU Radio. It's free software-defined radio. What really motivated this is I wanted a platform for experimenting with digital communications. I'm willing to spend some money to get the right hardware. I prefer not to have to spend $100,000 for my education. I'm willing to spend a few $1,000s for my education. I mean, really, the truth of this whole thing was, if you look at what's inside of secure phones, there's about 10% crypto and about 90% DSP. So I've been doing all this DSP. And then I thought, well, digital comm, this is where the future is. Let me go look at this. So I wanted a platform for experimenting with digital communications. I mean, look, it's pagers, it's the cell phones, it's the spread spectrum phones at home, it's the cable stuff. It's all digital communications. It's the way people are going. It's better spectrum utilization. It's really you get more stuff for less resources. And the other thing is we're doing this on commodity hardware. Now, there's a piece of this that you guys know about the DES cracker, the EFF was coordinated with, and Gilmore and Paul Kocher did a bunch of the work on it. To make a point that everybody who, for at least 5 years before, had read the papers about, here people, Mike Weiner from BNR, Bill Northern, had published a paper, about a 20-page paper that included a gate-level design for how to brute force DES, and included getting the quotes for the ASIC from the ASIC vendor and I mean, really, you could really say I could build this device that would solve these keys in so much time. But until people actually spent the money and built the thing, the export regulations didn't change. If you look at what happened, that piece of equipment got built, and all of a sudden DES was exportable within about 6 weeks. Because it's all the people that knew, of course, knew. The NSA, of course, knew. But sometimes it takes actually doing the thing to do it. So, but the downside of that is they built this custom piece of hardware that doesn't get any faster by itself. So, they spent, I don't know, about $250,000 to get the thing built. But, now it's sitting in somebody's basement, and it's not getting any faster by itself. Now, personally, I like the fact that AMD and Intel are like competing head-to-head. I mean, we bought these, it's almost been 9 months ago now, we bought these dual processor Athlons. I mean, they were at the time the fastest thing we could get. They're like the 1800 dual processor, you know, half a gig of memory, big disk drive, all this, you know, the burners, all that. It's like $1,300 from my local place. I'm like, wow. And that's going to get faster. I mean, it's already faster, already 9 months down the road. One more thing about that is I have built things using fixed point DSPs before, and they are a total pain to program. Turns out, like with these particularly with the fixed point DSPs, in reality, getting performance out of them, you have to code an assembler. And if you go talk to the guys at TI or Analog Devices, they'll tell you that. You talk to the apps engineer, and they, oh yeah, you know, you read the article, and yeah, we've got compilers for them. PS, you know, any product that's actually making any money was coded in assembler. Personally, I've had enough of that. So we want to transmit and receive any signal. We want this to be a practical environment. This is not just like some nice theory. I mean, MATLAB is cool. I can you know, draw really nice graphs, and we use it for developing big pieces of this. But it's not going to run in real time, and you know, we want this. And we want to also expand this whole free software ethic into what were previously hardware-intensive areas. Now, I've built hardware. I have put companies together to build hardware. I found it to be a very expensive way to do things. I mean, you got this funny stuff about hardware, like you're ready to build something and it's 19-week lead time on some part that you need. You know, it's like, ooh. Or, you know, gee, the tooling is $250,000 as opposed to, I mean, I remember when I was in college, I mean, that thing about, oh, software, it's like, it's how much complexity can you manage? There's nothing between, you know, you could, like if you're a civil engineer, I mean, I'm talking, I know to the choir here, but it's that thing about civil engineering, you want to try something out, you're not going to ever get to try it out. You know, you're not going to go build another, you know, Golden Gate Bridge. But in the software universe, it's like, yeah, well, what's between me and doing it? Well, my ability and who else I can find that wants to play. And hardware is kind of more on the bridge building. For those of you who have ever done it, it just doesn't go as fast. It's expensive. It's just a pain. So if we can turn more of this stuff into a software problem, we're all going to eventually be winning. If we get more people in the game, quicker innovation, we get new products that people didn't even envision, haven't envisioned. Okay, so what's required? Okay, this actually ought to be on our FAQ. So we're going commodity PC, faster the better. Some kind of RF front end. Now, again, if you look at our website, the truth is about GNU Radio right now, it's a work in progress. It is a set of tools. It is a set of like really sharp tools for at this point for people who have at least a pretty serious interest in radio. So we're not at the stage of the game where you just go buy this hardware and, you know, wow, I've got everything working. But anyway, we're doing the interesting thing from my point of view is this stuff where you use a wide IF bandwidth. Now, this means I can do the multi-channel applications and stuff. I can do things I can't do with the regular radio. I know in the ham thing, there's like the DSP-10. There's some ham radio transceivers that they've got quote DSP front end. They've got DSP in them, but in fact they're using a DSP only in the audio bandwidth. So they're really running like a fixed point DSP with a conventional audio codec, and they may be running their IF bandwidth is in the tens of kilohertz. Now, for example, if you look at any of the real contemporary communication stuff, that's not wide enough. So we've said right away, let's go. We're going to do relatively wide bandwidth stuff, but we still want to buy commodity hardware. So we're using an off-the-shelf, high-speed, relatively high-speed analog-to-digital converter at 20 million samples per second. Currently, just to get you an idea of what if there was some volume involved in here, right now Analog Devices is building A to D converters, which are really the crux of the whole biscuit here, that are designed for software base stations. They cost about $40. They'll sample at 80 million samples per second, 14 bits. So our ideal hardware, which is a couple slides down the road, but includes that kind of thing on a 64-bit PCI card. Because the PCs just keep getting faster and faster. Well, that's for the chip, but I mean, it's chip, small FPGA card, you know, it's like $80. It's not bad, but again, somebody's got to be willing to do it, you know, and build the hardware, and pony up the money. And now, there's also applications that people could use GNU Radio for that are single-channel narrow bandwidth. And we've got some interest in people in the amateur radio department here, some kind of pager demod kind of a thing where I have a relatively narrow channel that you could use an existing audio card, like a regular AC97 codec Or I know that there are people who are using the sort of one step up, the audiophile grade audio cards. I think they sample at 96 kilohertz, and they're stereo. So there's some folks who are building INQ demodulators in their RF hardware and then plugging it into the sound card. Most of us that are working on the GNU Radio haven't gone down that path. Turns out we've got the high-speed cards. We'd love for people to go do that. We'll make sure you have whatever infrastructure you need. So we're not saying don't go there. We're not going to do the work. So there's people in the mailing list that have posted things about here's a design, or go look at this kit from these people that's close enough, or you can pull the IF out of a scanner or some other tuner you have. Lots of ways around that problem. So in fact, if people were interested in that, then your hardware cost in the system is zero. It's effectively the PC you've already got with the sound card you've already got, plus like $25 worth of RF hardware that you bought as a kit or you soldered together. Okay. Now we're saying back on the ATSC, we're saying it's practical. And it's kind of got this caveat after having been at this for a little bit. In a year or two, I would say that it really gets practical. Part of the problem is that if you look at the symbol rate, the rate at which the symbols come across on the digital TV stuff, it's 10.76 million symbols per second. Most big pieces of that processing have to happen at twice that rate, so 21.52 million symbols per second. And there's times in there where you have like a 100 tap FIR filter. So you've got this 21 million times 10. And the number of MIPS you require starts climbing pretty fast. But anyway, for this $1,300, you can do 6 billion integer operations per second. The machines are super scalar, and on the interloop stuff, we've got assembler that we've written for a couple different things that really get us some pretty smoking performance. We're doing, those of you who know some DSP, doing floating point FIR filters, which are really like a dot product. The main loop is a multiply, accumulate, 2 fetches, 2 address increments. We're doing those in 1 tap per cycle. We can do better than that fixed point, but then it's you get the reduced range. If you look at also, just to give you an idea, those of you who actually look at DSP hardware, this is smokingly fast. This is faster than anything that the TIs in the world are selling you. And their machines, although they may use lower power, are really a pain to program. They've got like an 11, like if you look at the TI, the 6000 series part, they've got I think an 11-stage pipeline with no hardware interlock that you can screw yourself with. I mean, it's you can there's no hardware interlock. You can like reference stuff. Oh, this one needs 11 cycles later. It's complete. I've talked to people who've coded for that in assembler because the reality of the situation is they've got a pretty good compiler. But the reality of the situation is that the inner loops and stuff are still in assembler, and that is totally black magic. I mean, you think that like trying to get performance out of these superscalar, x86s, at least they always compute the right answer. You might not have optimal code, but at least it's computing the right answer. Okay, a little idea on computational requirements here. The 1080 interlaced, this is the transport stream processing. The decode on that takes about a half of a contemporary CPU. So figure that's on the neighborhood of 800 megahertz worth of Pentium or Athlon. Equalizer in some of these, you've got this thing where you got something on the order of 2.5 billion taps per second. You start multiplying these numbers together. So you need to get pretty smart about some stuff. What the equalizer is about is we have multipath interference. So particularly in a situation like the urban canyon, I mean, our chances of ever receiving HDTV in here are probably next to zero. Part of the thing that's come back with this HDTV is that you really need an external and outside antenna. The rabbit ears just don't get it. So we're kind of back to welcome to 1960 or something. The Viterbi decoder in here for doing the forward error, the decode on the forward error correction. It's about a million decisions per second. But again, there's some places in here where you can really win big on the SIMD stuff. And we've coded it all where we do, the bulk of the code is in C++. In cases where there's performance code that's related to different processors, there's a base case that handles it in C++, and then there's usually multiple versions of the assembler code. So, for example, we found on the Athlons that the 3D Now code is faster than the SSE by like a long shot. And again, it's classic Moore's Law thing. Even if we're off by little, well, it'll take care of itself. This is this idea on, again, this was mostly pitched at some engineering types from consumer electronics companies that, okay, now that we've convinced you that maybe people would do free software, well, how about open source hardware? And we pointed them at IP cores and these guys doing this, they've got PCI bridges and stuff that are all like with test vectors and really professionally done. This number is high. This thing could really be built, from talking to some other people. Total cost of manufacturing, I think, is probably about half that, about $40. But this was my really low quantity. Take a quick look at DigiKey, look at the websites. What can I buy today? I mean, you could get this $80 number with no problem. And what this gets you is this is like the ideal hardware for software radio. The FPGA, besides building the PCI bridge piece of the problem in here, actually can do some pieces of your signal processing. Some of the stuff that you can do, like channel selection, things that really turn out to burn quite a few MIPS on the PC, you could offload into the DSP, or into the FPGA. Printer, it's a PC board, it's a printed wiring board, is what it is. It's PC board. But the hardware guys really call them PWBs. Here's the easy way to find this. There's a mailing list, there's archives, there's a home page, there's links from the home page, but the easy way to, GNU Radio, one word, into Google, it's the top hit. We've got lots of fairly active. There's about 4 people actively developing the product. Matt Ettus was unable to be here today. He's a guy who designs Bluetooth chips for a living, and he's a great guy. He's done a bunch of amateur stuff with design of new protocols and new RF modulation strategies. He and I were kind of together saying, yeah, ATSC, it's a great hack. I mean, it's really, people were saying, no, you can't do it, it'll never work. And we're like, how hard can it be? Let me tell you, the problem is, I mean, if you're used to reading RFCs or something, or the IEEE specs, where it's like must, shall, test vectors here. The specs for the ATSC are really they're like you cannot believe. There's no test vectors for the thing. There's so many things that are subject to your interpretation, where there's really no clear cut. It had to go one way or the other. So there's cases where we've built a whole transmitter alongside the receiver. We're working top down from sort of like on the transmitter side. We got MPEG stream in, as far down we got, and then like cut over and then loop back up this way. And at the same time, we're working from the antenna towards. So we're working from the antenna up towards the MPEG, and we're also working from the MPEG down. We're going to hit in the middle. So, and we've got some known good transmitter output that was captured off of a commercial piece of equipment. So we know we've got known good input. We don't have to know the plain text behind it, but it's one of those where at least we know that it's got the right format and it looks really good. In general, or the truth is the transmitters are much easier than the receiver. We have software. The hardware that we have right now will only receive. There are cards available that will transmit. There's high-speed D to A cards that are very inexpensive that will go. We got enough problems making the receiver stuff work. It's a harder problem, and we at this point have sort of just dodged all of the regulatory issues. As soon as we start transmitting, we really need to be compliant. And there's places we could transmit. I mean, we could transmit in the 900 megahertz band or the 2.4 gig. And then this gets into a whole FCC thing about software radio, and they're proposing. The FCC at least is up to acknowledging that software radio is a pretty good thing. We haven't really put in their face, what about open source software radio? We just think it's not serving our interest to do that. Yeah? Yep. Well, okay, well here's the thing. We're building a toolkit. The reality is we're building a toolkit, box of tools. I mean, if we built a whole, we have not put together a whole application that looks like a scanner. If we put together a whole scanner, we could be compliant. We could say, if deaf, I'm in the USA, do not tune here. I mean, but seriously, this is the reality of the situation, folks. I mean, there is a breakdown in the old thinking. This is like paradigm shift that we're now getting to a place where people can have wide bandwidth hardware. And okay, are we going to crush the culture of innovation because of some lobbying that was done by some cell phone manufacturers because they didn't want to really fix the problem? And instead of fixing the problem, they created the foreign Espionage Empowerment Act. Thou shalt not build, sell, receivers. Yeah. Can you actually guys can come to the mic?
Step up to the mic.
Yeah, maybe I'll try to get, so it just is better later. Well, I think just keep talking. I think he's twisting an arm over there. Just try to.
Would you say there's any point in getting closer to the antenna than the tuner down converter, especially when we have seen MEMS coming through in a few years, which will have higher than 1 gigahertz response,
right?
Q factors that will allow channel selection.
Yeah, the closer, the better. I mean, it's a trade-off. So the closer we can get, the better. Right now, the analog to digital converters are the limiting piece. It's the dynamic range on the ADD converter. The spurious free dynamic range is the current problem. It turns out they work pretty well in the cellular band because those guys are all running power control. One of the places where it's really hard to do software radio well is a situation which you'd think would be the easiest one is like broadcast AM. Well, you might be, 5 miles from a 50,000 watt transmitter, right? And meanwhile, you're trying to listen to some guy that's, like 600 miles away, or it's nighttime and you're trying to listen to some guy that's halfway across the country. Now, you got this A to D converter that maybe he's got 14 bits, right? He's getting, the tall guy is just burning up your whole dynamic range. So that's the reality. And yeah, the converters are the whole thing. I mean, they basically start doing IF sampling also. It depends on how much bandwidth you really need for your application. So you can do what they call like passband sampling, which is I basically go direct from RF down to something I can feed into my A to D converter. We happen to be going, and the hardware we're using is a cable TV tuner module. We found it because it worked, it's cheap, it's off the shelf, it's got good specs. It will tune, it's basically designed for cable modems. It will tune from 50 megahertz up to about 890 megahertz. And it's got an intermediate frequency out, so it basically down converts down to a center frequency of 5.75, so it's 5.75 megahertz. And it's about 8 megahertz wide. And we've got a 20 megasample converter, so we can just pump that into there. Now, there's really, we're pretty much agnostic. I mean, then well, you can see if you do bandpass sampling. You can get. No, you have to be sampling at twice the bandwidth of interest. Okay, this is the thing where this is like if you look at what they're doing is it's not. If my bandwidth of interest is only this wide, but it's way up here, I still have to sample it like twice this wide. There's some corner cases that this thing works out in, but yeah, it's a question of how much do I want to deal with at the same time, and then do I have enough MIPS to make any sense out of it? Okay.
Your example was for the HDTV receiver. What would for the same thing? What would be an example of a chip that could handle 802.11 and Bluetooth at the same time? For example, would that be similar processor consumption or last more?
I haven't looked at that in detail.
Yeah.
I think that the 802.11 probably takes more processor, but the Bluetooth hops over a much wider frequency range.
And also, if you had two DSPs hooked up to the antenna, could you theoretically say, I want to tune into this way over here and this way up here? Is that why you need two DSPs? Or
you can do it all in the same processor. So I love the questions. I also want to get some. I have a representative from the EFF that I haven't even let speak yet. But But I want to get your question answered. The deal with the RF is we've got an IF bandwidth. It's however wide we can go. So we're currently running realistically about 8 megahertz wide. With these analog the analog devices parts, we could sample up to say 80 million samples per second, which get a 40 megahertz wide chunk. Now, once I've got this it's like I'm sampled at 80 million samples per second. There are 16-bit samples typically, and now I don't really need DSP. I just need enough horsepower somehow. So I can have a bunch of PCs racked, a bunch of 1U dual processors with gig Ethernet behind them would work. Yeah, and then I just throw those at it. Okay, that good?
Yeah.
Okay, can you hold on? I want to give you the. This is great, and we'll be available to talk after. But Ladrina is here. I'm sorry, I'm really. Here's the thing. The BPDG is the Broadcast Protection Discussion Group. Now, out of the Copy Protection Technology Working, this is like acronym city. Go to blogs.eff.org. There's a weblog on there that's called Consensus at Lawyer Point that really spells out in gory detail what happened. The high points of this deal are the content people, most of the movie folks, are saying, hey, we're not going to release any content unless we can keep people from making copies of it and doing what they like. It's a slight exaggeration, but not much. So what they want to do is they want to set in this MPEG transport stream that's transmitted in the clear broadcast, right, free TV. They want to set a bit in this transport stream that they're calling the broadcast flag. Then what they want to do is they want to have all the consumer electronics folks honor this bit that says thou shalt not copy. Then they want to pass some laws banning non-compliant receivers. So this is their three-part strategy. Now, at the invitation of the EFF, I went down to this meeting, talked to these nice people. It was like the nicest group of people I'd ever met that want to make sure we can't do what we want to do. Really, they're like very polite and really lovely people. It's like going to the UN. They've got, it's like lawyer, technology guy, lawyer, technology guy, lawyer, technology guy, and it's in big concentric views, and you go do your pitch. But that's what they're up to. Now, please, say more. Yeah.
They're soliciting public comments for this big public workshop they're going to have on Wednesday in Washington in the Commerce Department on this. Technologyadministration.doc for Department of Commerce.gov.
Great.
You'll find it there.
Very good. Thank you.
Okay. All right. I'm going to move on to the 5-minute discussion of what exactly the BPDG is and what they're trying to do right now. Basically, they're a subgroup of CPTWG, which is a copyright group. And this is all started by 5C companies. 5C companies being an organization of 5 companies, including Hitachi, Intel, Toshiba, Sony, and Matsushita. And basically, they've been created to, exactly as Eric said, address this problem of making digital copies of content. So basically, they have no bylaws in this group. It's theoretically an open group. There have been lawyers, there have been technologists. They've all been sitting in on these discussions since late last year. But strangely enough, these 5 companies who have founded the group are the only ones in the end whose technologies have been approved by this working group. So that's your first tip-off, to say that something's going on here. Something strange is something's not right. And basically, we're having all of these great technologies come out. I mean, you can receive and transmit any signal, ideally. And these people are going to make it so that that's not really going to be the case. For instance, right now with analog TV, you can receive any signal that you want. You can copy it to a VCR. You can do what you want. But when TV goes digital, that's not going to be the case. So, for instance, in 2006, if 85% of the consumer market can receive digital signals, TV is going to go digital. Digital TV will be the standard. So here's the problem with that. These companies got together and they said, we have a problem. We're going to have people pirating our stuff. We want people to watch our content. MPAA basically says, we want people to watch our content in the way we want it to be watched, when we want it to be watched. So here's the problem. They wanted to address 3 issues. And basically, they wanted to cover recording. They wanted to cover the ways that approved devices will basically get approved. And they wanted to make everything tamper-proof and tamper-resistant. This is going to deter tinkering. This is going to deter things like GNU Radio from being able to exist. So here's how they're going to address it. They're saying every digital transmission is going to contain a broadcast flag. Either a 1 or a 0 will be in every transmission at the beginning of every frame. And if there's a 1 in this transmission, that means it can't be recorded, it can't be copied, it can't be redistributed. If there's a 0... Yes.
Promises not to transmit it anywhere except to another approved box.
Sorry,
so there's like a cartel. It's really a cartel, and it's patent cross-licensing kind of deal.
Yeah, so you can record to approved technologies, but you're pretty limited. You're very much more limited in what you can do with what you've recorded than what's going on now. Their second point that they want to address is that they want to plug the analog hole, which sounds a little odd, but if you go to the EFF site, there's a great paper that you should read about this issue. It basically means that there's this analog is a threat to digital media. Let's say you have some sort of digital media, you can copy it onto some analog media and then back into digital. Like this digital media really needs to be protected, and companies and MPA is saying, oh wait, hold on a second, we've got this issue of all this legacy hardware that's going to circumvent this. And the final thing is that they want to control peer-to-peer. Basically, they're saying, well, we think digital copies are going to get out there somehow. We've got to control it. We've got to control Nutella. We've got to control everything, all sorts of peer-to-peer software. And basically, that's not going to happen. So, in short, they want to control computers, they want to control analog to digital converters, and they want to control the internet. And so, this is obviously bad, but I'll just say very quickly, throughout history, technology companies, all sorts of technologies, have been allowed to innovate. You've got piano rolls, you've got radio, you've got satellite TV. Look what happened when industries were regulated. What happened to DAT? DAT failed. CDs were not regulated. CD technology took off. Betamax. Betamax was regulated. VCRs are a huge success today. Basically, this is the first case of technology companies giving in to the MPAA, giving in to industry and saying, well, we'll try to meet you halfway. We'll try and compromise. Historically, this has allowed technologies to fail, and this is a path that we cannot go down. So basically, projects like GNU Radio will not be allowed under the BPDG. And also, in short, it's bad for free software, it frustrates fair use, it's bad for innovation, it's bad for competition, and basically this will just delay digital television adaptation in the marketplace. So basically, we need to stop this. The BPDG final report was just released. You can read it on the EFF website. And basically now this report is going to go to Congress. By the way, Microsoft and Philips were not part of the original process. They've been at these meetings, and they have filed reports saying we do not support this. So this shows there are other companies out there who are trying to fight this. But you should find out about the BPDG, find out about digital TV and all these issues, because it's going to go to Congress, and this is something that we can help stop so that we can support innovative software like GNU Radio.
All right, thank you very much. It's the end. I'll be in the back or probably out in the hallway, and we'll take questions. I know there's plenty more questions. I'd love to talk to you about all this stuff. So the EFF website on the politics and our GNU Radio software is there. Come on down.